Hey guys, welcome to Based Physics. In this course, I'm going to be talking about waves and interference. So here what we have is one wave. What I want you to do is get as close as you can and stare right into the red circle. Slowly back out and look around. Are things waving around? Well, if you did it for 30 seconds, they actually might. So that might be kind of cool. But for now, we're just going to move on. So, what causes this? So essentially what causes this is this red dot right here is something oscillating in a medium. So let's say that this is water. And so the different colors on that represent the peaks and the valleys of the wave. And so you might recognize this from seeing like a rock or something like that. When you throw it into the water, it causes that pattern, right? And so what happens if we add a second rock or a second oscillation? See, so what that does is it creates this pattern, and they cause destructive and constructive interference when waves are in phase. And what in phase means is that essentially they line up with each other. So if you think about a wave, what's the shape of the wave? It's kind of like an S shape like this, like up and down, right? And so what that means is that when a wave is laid on top of another wave in the same manner and direction, it causes it to be bigger. But if it's on the opposite side, they neutralize each other. And so that's what's happening. So in these dark sections, they're neutralizing each other, but in these light sections, they are keeping each other afloat. So you know that they are in phase if their path difference is equal to an integer times the wavelength. And that might sound complicated, but if that doesn't make sense, just think about how if a wave completes its cycle, that is one wavelength, right? So let's say it starts in this red dot on the left, completes its cycle one time, and makes it to this red dot. Essentially, that would mean that the wave is starting here at the same spot, so it causes that constructive interference. But if they're half a wavelength away, they interfere with each other and they cause each other to cancel out. And so what you can do is you can label these. So 0 lambda is the top one, then half lambda, 1 lambda, 1.5 lambda, 2 lambda, and so on. Oh, and lambda is just the symbol for wavelength. If you ever see it, it's like a Greek letter, kind of looks like the legs of a stick figure. However, these perfectly positioned oscillators, these red dots, are not really realistic. Like, in what real world do you have these things happening? So in this case, what you have is you have something called diffraction. And diffraction happens when a bunch of light is pushed through a tiny slit or something like that. And you can see diffraction in everyday life. Like if you ever have a door and you have it open just a tiny little bit, then the light coming through will come out kind of in like a pattern of like an array of lights. And why that happens is because of diffraction. So what happens in diffraction is all the light goes through that hole and then it kind of gets spread out as it reflects off of the sides of that hole. And it creates a pattern that looks something like this. And so a typical diffraction pattern, it kind of has these layers, right? So here it's strongest kind of right in the middle, and as you get further out, it gets lighter. And that's because most of the light is reflected straight forward, but some of it is reflected off and over to the sides, and that's why it gets darker because there's less actual light that's going through there. However, something that you are going to see in AP Physics especially, and pretty famous experiment is called the double slit experiment. I think the double slit experiment is actually pretty cool. I would recommend that you guys research it more if you're interested, but this is going to be what the double slit experiment looks like. So this right here is a really good depiction of what the double slit experiment is. And so see, you have your initial wave source that can be caused by something, and then you have these two slits. I just want to say that it's not necessarily to scale with this picture. Usually the slits are very, very tiny, not relative to the wavelength. And so, interestingly enough, these two slits right here, they kind of create their own sources. So source A and source B are kind of created by these slits. And what that causes is it causes another pattern of two source interference. And so what that means is that it is a diffraction pattern caused by the slits with a two source interference laid over it. So if you can see the wave intensity thing right here, the waves are still the most intense in the middle, but here they still have these like half lambda, 1 lambda instances of constructive and destructive interference. And so this is a pretty common question on physics tests, and especially AP Physics. And so I think it's important to know the two slit experiment and how to interpret it and how to understand it. So something that you can actually do with double slit interference is you can calculate, pretend that this area where we have Y, this is some kind of screen or something like that where the waves can be projected onto it. So what you can do is you can calculate where on this screen there's going to be maxima and minima caused by constructive and destructive interference by using these equations. So here we have D, which is the split between the two different sources, the distance between the sources, and here we have theta, which is the angle from the middle to whatever minima or maxima it is. In this case, the diagram shows kind of near a minima, but it isn't always going to be like that. And something that you can do is you can figure out that the ratio between y and d is the same thing as sine of theta, because this angle right here, this theta, is going to be very, very small in this case. And physicists love to simplify things, so they just say that tan theta is equal to sine theta in very small angles, which they're not exactly the same, but they're close enough that physicists don't really care the difference that much. And so that way you can find that tan theta is equal to y over d. So then you can find where a maximum is when d sine theta equals m lambda. And what that means is that the distance between the sources times sine of the angle, which is equal to tan of the angle in this case, is equal to m times the wavelength. And m is just an integer, right? Because we remember that sources of constructive interference are always at integers, and destructive interference is always at half integers, like 1/2, 3/2 in two source interference. And so then what that means is that if you plug in everything into the equation, you can figure out what y is by using m lambda times d over d. And that's just how you find the equation. So let's say that you're looking for the source of interference at 1 lambda, right? So that would be this one out here because it's 1 away. And so you plug in 1 times lambda, whatever the wavelength is, times d over d, and that will calculate how far this distance is. So that's kind of a cool thing that you can use to figure out how to do that. I like to try to reason my way through things and not necessarily just blindly use an equation, so I hope kind of explaining that equation helped you guys. That's going to be all on waves for this video. There are some more things that you can do on waves, and I would be happy to do some more things, like there's thin film reflection and more than two source interference that I could go over. But yeah, this was my first video, so if there's any feedback that you guys have, I would love to hear it. Thanks, and I'll see you next time.